Two ancient wonders stand worlds apart yet speak a silent, similar language. The Great Pyramid of Giza and the walls of Machu Picchu were built by cultures separated by vast oceans and thousands of years, yet they used eerily similar methods to move and shape mountains of stone. This video explores the captivating enigma of the cross-cultural origins of monumental stone building techniques. By the end, you will see these ancient sites not as isolated marvels, but as chapters in a single, interconnected human story. How did builders across the globe develop the same solution for fitting multi-ton blocks with knife blade precision? Could a shared, forgotten wisdom explain the identical stone knobs found from Peru to Lebanon? We will delve into the global patterns of polygonal masonry, the mysteries of megalithic transport, and the possibility of a deep ancestral knowledge. What does it say about us that the same dream of building in stone emerged again and again across the ancient world? The true wonder lies not in the stone itself, but in the impossible choice the builders made. Imagine for a moment a simple wall. The easiest way to build it is with small, uniform bricks, manageable for one person to carry and set. Now imagine choosing instead to quarry a single rock the size of a car. You must somehow move it, lift it, and then carve its neighbor from another mountain to fit against its first irregular face. This deliberate selection of the most difficult path possible is the heart of the megalithic mystery. When we speak of monumental architecture, we are speaking of a conscious decision by a society to invest generations of labor, ingenuity, and collective will into a single, enduring statement. The scale is one clue, but the precision is the real signature. A massive, rough-hewn block is just a boulder. A massive block carved to interlock perfectly with another, often without any binding mortar, is a message. It whispers of a mastery that goes beyond mere construction into the realm of high art and profound intent. This artistry takes two primary forms that we see echoed around the world. The first is often called cyclopean or polygonal masonry. Here, the builders used stones of many shapes and sizes, each one uniquely carved so that its edges match the contours of the stones around it, creating a jigsaw puzzle of immense weight and strength. The walls of Sacsayhuamán in Peru or Mycenae in Greece are breathtaking examples. The second is ashlar masonry, where stones are cut into clean, rectangular blocks and stacked with such thin, precise joints that you cannot slide a piece of paper between them. The casing stones of the Great Pyramid before their removal reportedly displayed this impossible perfection. By understanding these technical definitions, we create a common language. It allows us to look at the sun-drenched terraces of Ollantaytambo in the Andes and the submerged foundations of Yonaguni in Japan and ask the same fundamental question. Why did cultures with no apparent contact arrive at the same breathtakingly complex solution? Recognizing this shared architectural vocabulary is the first, crucial step in listening for a conversation that might have spanned the entire ancient world. This shared architectural vocabulary finds its most dramatic expression in the art of the polygonal wall. High in the Andes of Peru, the fortress of Sacsayhuamán presents a staggering sight. Its walls are composed of colossal limestone blocks, some weighing over 100 tons, each one a unique, irregular polygon. These stones are not simply stacked. They are carved with such meticulous care that their edges meet in a seamless, interlocking embrace. The joints are so tight that, as many observers note, not even the thinnest blade of a knife can find its way between them. The effect is less like a constructed wall and more like a section of the mountain itself, reshaped by some titanic, intelligent force. It is a masterpiece of patience and precision, built to endure for millennia. Yet, travel across the vast Pacific Ocean to the island of Japan, and you will find a quiet echo of this same impossible technique. At the Sacsayhuamán shrine, rebuilt in the early 1700s, the stone foundations display a strikingly similar polygonal masonry. The stones are smaller, the scale more human, but the principle is identical. Multi-sided blocks are individually shaped to fit their neighbors perfectly, creating a sturdy, mortar-free base. The parallel is uncanny. Two cultures separated by the greatest ocean on Earth, separated by thousands of years of history, arrived at the same breathtakingly complex solution for building with stone. The question of why is where the mystery deepens from coincidence into potential insight. This was not merely an aesthetic choice. Polygonal masonry is a brilliant feat of passive engineering, particularly for regions prone to the Earth's tremors. In an earthquake, a rigid wall of uniform bricks is vulnerable. The seismic waves can travel through it, causing it to crack and collapse along its straight, weak mortar lines. But a polygonal wall is different. Its interlocking, jigsaw-like structure is inherently flexible. When the ground shakes, the irregular stones can shift and settle against one another, dissipating the energy throughout the entire structure. They move as a single, resilient unit, then settle back into place. This understanding of dynamic load and structural integrity represents a profound knowledge of how stone behaves under stress. It is knowledge that seems to have emerged independently in both the seismic heart of the Andes and the earthquake-prone islands of Japan, so we are left with a powerful duality. On one hand, we can marvel at the genius of human innovation, at the capacity of brilliant minds in isolation to discover the same elegant solution to a shared environmental challenge. It speaks to a universal logic in the language of physics and material. On the other hand, the specificity of the technique, the deliberate choice of the most labor-intensive method possible to achieve this specific, resilient result whispers of a deeper possibility. Could it be that this represents not just parallel invention, but a fragment of a much older, widely dispersed understanding? The walls themselves offer no written testimony, only their silent, enduring fit. These resilient walls, however, are only half the story. To understand how such impossible stones were even put into place, we must look closer at the blocks themselves, where a second, more intimate parallel emerges. Scattered across ancient sites from South America to the Mediterranean, you will find a curious and consistent feature: small, protruding stone knobs, often called bosses or nubs, and their counterpart, carefully carved indentations or grooves. At the mighty Peruvian site of Ollantaytambo, many of the rose-colored granite monoliths feature these rounded protrusions, seemingly left rough while the surrounding stone is finished smooth. Travel across the world to the legendary quarries of Baalbek in Lebanon, home to the largest cut stones on Earth, and you see the same peculiar bumps on the famous stone of the pregnant woman. Even in the ancient Egyptian quarries at Aswan, similar handles appear on the sides of the unfinished obelisk. For a long time, the accepted explanation was simple. These were just unfinished quarry marks, places where the stone was left attached for transport and would be chiseled away to a flat surface at the final building site. But a growing number of researchers and engineers find that explanation incomplete. Why would builders go to the extraordinary effort of shaping a block with knife-edge precision on 5 of its 6 sides, only to leave a clumsy, protruding knob on the last side if it was merely waste to be removed? It seems an odd and inconsistent choice for cultures renowned for their meticulous craftsmanship. This has led to an alternative theory, one that sees these nubs and grooves not as accidents, but as the fingerprints of a forgotten technology. Imagine these protrusions as integrated handles. Ropes could be looped around them, or wooden levers could be slotted beneath them. giving workers critical purchase points to pivot, lift, and guide multi-ton blocks with far greater control than if they were trying to grip a sheer, flat face. The grooves and indentations found elsewhere could have served a similar purpose, acting as anchor points for a complex system of ropes and counterweights. Some even suggest these features hint at a form of ancient crane technology, where large frames or A-frames were used in conjunction with these stone handles to achieve the precise placement we marvel at today. If this theory holds water, its implications are profound. It suggests that beyond a shared style of wall building, there may have been a shared, standardized toolkit for megalithic construction, a common set of solutions to the universal problems of weight, friction, and gravity. Whether this toolkit was developed independently by brilliant minds facing the same physical constraints, or whether it represents the scattered pages of a much older manual, is the enduring enigma. These silent stone handles offer no easy grip on the truth, only a tantalizing clue that the world's ancient builders might have been speaking the same silent, practical language long before the first written word was ever carved. The precision of these stone handles would have been useless without an equally precise method for the final, delicate act of placement. Here, a third and remarkably subtle parallel emerges in the ancient stoneworker's toolkit, the beveled edge. Look closely at the corners of the most finely fitted stones around the world. On the colossal granite boxes within Egypt's Serapeum of Saqqara, and on the shattered andesite blocks scattered across the high plateau of Pumapunku in Bolivia, you will often find the same thoughtful detail. The sharp 90-degree edges of the stone are not left raw. Instead, they are carefully cut back at a slight angle, creating what craftsmen call a bevel or a chamfer. At first glance, it might seem like a simple finishing touch, a minor aesthetic choice. But this is where the ancient builders reveal another layer of their deep, practical wisdom. This subtle shaping is engineering in its purest, most elegant form. Think of moving a heavy piece of furniture into a tight space in your home. The sharp corner is the enemy. It catches on the doorframe, it scrapes the wall, it resists your every effort to slide it into its final position. Now imagine that corner is gently angled. Suddenly, the object glides more easily. It finds its path with less friction and far less risk of damaging itself or the space it is entering. This is precisely the purpose experts believe these ancient bevels served. During the monumental task of transporting a 100-ton stone block, a sharp edge is incredibly vulnerable. A single bump or impact could chip or fracture that perfect corner, ruining the precise fit the builders worked for months to achieve. A beveled edge acts as a built-in bumper, sacrificing a small, unimportant portion of the stone to protect the critical geometry of the joint, but the brilliance continues. Once the block arrives at the wall, that same bevel can act as a guide. As the stone is painstakingly lowered into place, the angled edges help it slide against its neighbors, directing it into its final, tight position. Some researchers even suggest that for blocks designed to fit together under immense pressure, these bevels could create a kind of compression seal. As the weight of the stone above settles, it would force the angled faces together, locking the joint with even greater intimacy. The widespread use of this specific, technically sophisticated detail is a quiet revelation. It moves beyond grand style into the realm of refined, iterative problem solving. It shows a culture that did not just learn how to move big rocks, but one that perfected the process through generations of trial, observation, and accumulated physics. They understood friction, they understood material stress, and they developed a simple, repeatable solution to manage both. This points to a knowledge so deeply embedded in the craft that it became instinctual. So we must ask, does the global presence of the beveled edge signal a moment of parallel genius, where separate cultures all realized the same simple trick for protecting their stonework? Or does it hint at something more foundational, a core principle in a lost school of megalithic engineering, a fundamental rule passed down and applied wherever humans dared to build in stone. The answer remains locked in the angle of the cut, a silent testament to a level of care that transforms brute force into an act of profound finesse. The choice of stone speaks as clearly as the shape of the wall. Across continents and eras, ancient builders displayed a consistent, almost stubborn, preference for the most challenging materials imaginable. The Egyptians did not merely carve their iconic obelisks from any available rock. They journeyed hundreds of miles up the Nile to the quarries at Aswan to extract monolithic shafts of rose-red granite. High in the Andes, the Inca shaped their most sacred temples from andesite, a volcanic stone of immense hardness. At Göbekli Tepe in Turkey, the world's oldest known megalithic site, creators 10,000 years ago erected towering pillars not of soft sandstone but of dense limestone. This was not a matter of convenience. Transporting and shaping these materials with stone, copper, or bronze tools represents a task of almost unimaginable difficulty. So we must ask, why choose the hardest path? The first and most obvious answer is permanence. Granite, andesite, and basalt are igneous rocks, born from the immense heat and pressure of the Earth's interior. Their interlocking crystalline structure gives them incredible density and resistance to weathering. A sandstone statue might erode in a few centuries under wind and rain. A granite one can stand for millennia, its inscription still legible, its form defiant against time. These builders were not just constructing for their own generation. They were laying down markers intended to speak to the distant future, to become eternal parts of the landscape itself. Their choice of material was a declaration of intent: this will last. But permanence alone may not tell the whole story. To understand the deeper pull of these stones, we must consider their origins. Granite is not just a hard rock. It is literally a piece of the deep earth, the very foundation of continents brought to the surface. Andesite and basalt flow from the hearts of volcanoes, material born of the planet's most primal creative and destructive forces. To build with these substances is to incorporate a piece of the living earth, the bones of the world, into a human creation. This suggests a powerful symbolic layer. The structure is not just on the land, it is of the land, a permanent fusion of human will and terrestrial power. Some researchers have pointed to other, more subtle properties. Certain types of granite have been noted to conduct vibration and produce resonant frequencies. Could the choice of material have been influenced by an ancient understanding of acoustics, a desire to make spaces that hummed with a specific energy during ceremony? Others explore the concept of geopathic stress, the idea that the earth itself has energetic lines, and that certain stones placed in certain alignments might interact with these forces. While these ideas move into speculative territory, they stem from a valid observation. The builders' relationship with their material was profoundly intimate. They knew the grain of the stone, the sound it made when struck, the way it fractured under pressure. Their selection was never arbitrary. It was a dialogue with the substance of the world. So we are left with a material mystery that mirrors the mystery of technique. The global preference for igneous and metamorphic stone points to a shared human recognition of what endures. It reveals a universal reverence for the deep earth and a universal ambition to create legacies that would outlast empires, languages, and gods. Whether driven by symbolism, physics, or a spirituality woven into the landscape, this consistent choice underscores a profound truth. For these ancient cultures, the medium was not just a means to an end. The stone itself was the message. The hardest stones in the world are useless if they remain in the quarry. This leads us to the most physically daunting chapter of the story, the transport conundrum. How did ancient cultures move the unmovable? From the deserts of Egypt to the mountains of Peru, the folk tales echo one another. Stories speak of stones that glided on sound, that were lifted by song, or that walked to their resting places guided by magic. While these legends capture the awe the process inspired, the practical reality presents a puzzle of epic scale and brute force ingenuity. Let us compare the most compelling theories from around the world, not to find one secret answer, but to witness a shared spirit of problem-solving. In ancient Egypt, tomb paintings and archaeological evidence point to a method of breathtaking simplicity and staggering effort. For the great obelisks and pyramid blocks, the primary tool appears to have been the wooden sledge. A massive stone would be lashed to a giant sled. Then, teams of workers, sometimes numbering in the hundreds, would pull it along prepared causeways. The genius twist revealed by experiments and a famous mural was likely the use of a liquid lubricant, pouring water, or more effectively, a slurry of wet clay, in front of the sledge runners dramatically reduced friction, turning a near-impossible drag into a manageable, if still Herculean, pull. This was logistics on a national scale, a triumph of coordinated labor over raw physics. Across the ocean in the Andes, the challenge was even more topographically severe. To move multi-ton blocks from quarries to mountaintop citadels like Ollantaytambo, the Inca likely employed a different yet equally clever toolkit. The most widely accepted theory involves a combination of earthen ramps and log rollers. Stones would be levered onto a bed of parallel logs. As teams pulled from the front, other workers would constantly retrieve logs from the back and place them in front, creating a continuous rolling path. For steep inclines, immense temporary ramps of soil and rubble were constructed, turning a vertical problem into a long, gradual slope. The coordination required was immense, a silent ballet of motion and counter-motion. Then there is the most evocative legend of all, from the remote isolation of Easter Island. Oral tradition and modern experiments suggest the island's iconic Moai statues, some weighing over 80 tons, may have literally been walked to their platforms. The theory proposes that teams used a system of ropes to rock the statue from side to side, pivoting it on its base, inching it forward with each rhythmic tilt. It would have been a slow, precarious, and incredibly dangerous dance, giving literal life to the idea of stones walking across the landscape. This method stands in stark contrast to the Egyptian or Andean approaches, yet it solves the same fundamental problem with the materials at hand: rope, human strength, and profound patience. The striking similarity across these cultures is not a single magic technique. No universal blueprint for moving megaliths exists. The similarity lies in the universal nature of the challenge itself: gravity, friction, and distance, and in the innovative, intensely human solutions devised to overcome it. Each culture looked at their environment, at the resources they had, and engineered a method that worked. The Egyptian solution leveraged water and mass labor on flat desert ground. The Andean solution mastered inclines with ramps and rollers. The Polynesian solution on a treeless island turned to dynamic motion and rope. This points not to a shared instruction manual, but to something perhaps more profound: a shared pragmatic ingenuity. It reveals that when faced with an impossible task for a sacred purpose, the human mind, in isolation after isolation, finds a way. The magic was not in floating stones. It was in the collective will to make them move. The silent surfaces of these stones hold a secret dialogue, etched in the subtle scars left by their creators. To trace the origins of these global techniques, we must become detectives of the microscopic, examining the tool marks that are the true fingerprints of the ancient builders. The debate they ignite is one of the most fascinating in archaeology, centered on a single, compelling question: what exactly were these people using to cut rock like butter? In Egypt, the interiors of granite sarcophagi within the Great Pyramid and the boxes in the Serapeum present surfaces of confounding smoothness. The flatness is so precise, the corners so sharply defined, that to the modern eye they appear almost machined. Similarly, in Peru, at sites like Ollantaytambo, we find andesite blocks with intricate, shallow channels and perfect right-angle cuts that seem to defy the presumed capabilities of bronze or stone tools. The immediate, visceral reaction is to wonder about lost technologies, advanced diamond-tipped saws, or powerful, unknown machinery. Yet, the mainstream archaeological explanation offers a different, though no less impressive, narrative. It points to the incredible efficacy of simple tools paired with profound patience and clever physics. The primary method is believed to be abrasion, not cutting. Workers would use a sawing or grinding motion with a copper blade or a piece of harder stone, constantly feeding an abrasive slurry of wet sand, often quartz, which is harder than granite, into the groove. The quartz particles would become embedded in the softer copper, creating a durable, effective cutting edge that, over weeks or months of relentless work, could slice through the hardest stone. This method leaves telltale marks, parallel striations in the stone from the back and forth motion of the saw. For drilling, the same principle applied. A hollow tube of copper, perhaps weighted and turned with a bow drill, would be used with the same abrasive sand. As it ground its way down, it would leave a cylindrical core of stone inside the tube. This is not just theory. We have physical evidence, granite core samples from Egyptian sites, like the one in the British Museum, which show the clear, spiraling groove left by the abrasive drill bit. The core itself is a snapshot of the process in action. The existence of these cores proves a sophisticated understanding of rotary motion and persistent force. It does not require alien technology, but it does demand we radically recalibrate our appreciation for what dedicated human labor, guided by generations of accumulated craft knowledge, could achieve. The real mystery, then, may not be in a single magical tool, but in the scale and consistency of the skill. Could such a labor-intensive, time-consuming method really account for the thousands upon thousands of perfectly worked blocks at these monumental sites? This is where the debate finds its fertile ground. Some researchers examining the tool marks note features that seem unusual for simple abrasion. They point to drill holes in Egyptian granite that show a consistent, rapid feed rate. The drill bit appears to have moved through the stone with a speed and uniformity that a manual, sand-based drill might struggle to achieve. They observe corners that are impossibly sharp, with no sign of the rounding that might be expected from a manually guided sanding process. These observations do not necessarily point to lasers or power tools, but they do open the door to considering more efficient, possibly lost mechanical aids. Perhaps the ancient world had developed more advanced forms of the bow drill or even simple gear systems that we have not yet discovered in the archaeological record. The comparative study of these marks across the world is where the plot thickens. Do the striations on a basalt block in Peru match the pattern found on a granite slab in Egypt? Is the signature of a tubular drill in Lebanon identical to that in Mesopotamia? If consistent, identifiable tool signatures were found across disparate continents, it would be a thunderous clue pointing toward a shared technological source, a transfer of knowledge. To date, such a clear, smoking gun has not been widely recognized by mainstream scholarship. The marks suggest independent cultures arriving at the same brilliant, abrasive solution, the universal language of sand, patience, and rotary motion. Yet, the haunting perfection of the work leaves a sliver of doubt, a whisper that perhaps we are still not giving our ancestors their full due. The stones will not say what tool was used, only that the hand that wielded it possessed a mastery we are still striving to fully comprehend. The silent mastery of stone finds its ultimate expression not just in how it fits together, but in where it points. Across the ancient world, the grandest structures consistently share a hidden dimension. They are built in conversation with the sky. Stonehenge frames the rising summer solstice sun. The Great Pyramid's sides are aligned with near-perfect cardinal directions. The Coricancha, the Inca's golden temple in Cusco, was designed so that sunlight during the solstices would illuminate specific sacred niches. This is no coincidence. It reveals a motivation far deeper than mere shelter or defense. These cultures were constructing permanent, physical models of the cosmos itself. The stone was their medium for anchoring the chaotic, flowing patterns of human life to the stable, predictable cycles of the heavens. It was an act of profound symbolism, a way to declare that earthly power, whether of a king or a community, was sanctioned by and synchronized with the fundamental order of the universe. Achieving this celestial alignment, however, transformed a symbolic ambition into a monumental technical puzzle. To make a temple doorway capture the first ray of dawn on a single specific day of the year requires astonishing precision over vast distances. Imagine the challenge. A team of builders must first identify a distant, fixed point on the horizon where the sun will rise on the winter solstice, for example. Then they must survey a line, potentially miles long, from that horizon point back to the intended temple site. Finally, they must construct the doorway so its axis perfectly matches that surveyed line, a task requiring absolute accuracy in both measurement and masonry. This implies a sophisticated knowledge of astronomy, of course, but also of advanced surveying and geometry. They were effectively doing celestial trigonometry with ropes, stakes, and simple sighting tools. The Great Pyramid's near-perfect north-south alignment, with an error of less than a fraction of a degree, is a feat that would be impressive even with modern instruments. This shared technical requirement, the need to translate cosmic observations into immovable stone, creates a compelling common ground. It presents a universal problem set. How do you measure the angle of a star? How do you project that angle onto the ground? How do you build a structure that will hold that alignment for centuries? This confluence of cosmic ambition and earthly engineering may be a key to understanding the parallels in their methods. The drive to build with such precise, enduring stone was not separate from the drive to map the heavens. They were two sides of the same sacred coin. You cannot create a reliable, permanent astronomical observatory from wood or mud brick. Those materials shift, warp, and decay. To create a calendar that would last for generations, to build a clock that used the sun and stars as its gears, you needed a material as timeless as the cycles you were tracking. Granite, basalt, and andesite became the only suitable canvas. This necessity could have naturally led diverse cultures toward similar engineering solutions. The need for perfectly flat surfaces to serve as sightlines, the need for perfectly square corners to establish true cardinal directions, and the need for joints that would not settle or shift over centuries. All of these precise requirements would have pushed builders toward the same technical ideals: flawless flatness, tight interlocking fits, and monolithic stability. In this light, the global similarities in polygonal masonry or perfect ashlar blocks might not stem from a shared, secret blueprint. Instead, they could be the inevitable, convergent results of different cultures grappling with the same ultimate challenge: how to build a mountain that speaks to the stars. The stones were not just placed, they were aimed. And in that act of aiming, we see a unifying human impulse to find our place in the cosmos and to chisel that understanding into the very bones of the earth. This cosmic ambition to build in stone forces a fundamental question about human history itself. Did this shared dream of perfect, aligned architecture arise separately in the minds of isolated cultures, or was it a single idea that traveled the world? This is the great theoretical divide at the heart of our mystery, the debate between independent invention and cultural diffusion. On one side stands a powerful and elegant argument for human ingenuity in isolation. This view, supported by mainstream archaeology, suggests that humans are brilliant problem solvers. When different societies face the same fundamental challenges, the need for stable shelter, the desire to express communal power, the impulse to honor the divine with enduring monuments, they will, through trial and error, often converge on similar solutions. It is a principle we see throughout history. Pyramidal structures, for instance, are not just in Egypt and Mesoamerica. They appear as burial mounds in China, as temple platforms in Mesopotamia, and as ceremonial earthworks in North America. The pyramid is simply the most stable way to build something very tall out of stacked material. It is a shape dictated by gravity itself. In this light, the similarities in stonework could be seen as a similar convergence. The problem of fitting large stones tightly to withstand earthquakes or time leads logically to interlocking polygonal shapes. The challenge of moving massive weight suggests the use of ramps, rollers, and lubricants. Separate cultures working with the same laws of physics simply arrived at the same logical conclusions. There is a beautiful democracy to this idea. It credits every civilization with its own innate genius, born of its unique environment and needs. The opposing perspective wonders if that explanation is too neat. Proponents of cultural diffusion listen to the echoes between these sites and hear not a chorus of separate voices, but a single melody passed from one land to another. They point to the ocean not as a barrier but as a highway. Ancient maritime cultures like the Phoenicians were known to trade across incredible distances as early as 3,000 years ago. Could knowledge have been a trade good as well? Currents and winds create natural routes across the oceans. The Pacific's currents, for example, could have facilitated contact between South America and Polynesia long before recorded history. This is not about sunken continents or alien visitors, but about the very real, though poorly understood, seafaring capabilities of our ancestors. They look for clues beyond architecture. Are there similarities in artistic motifs, like the stepped spiral or the double-headed serpent, that appear in both the Old World and the New? Do linguistic patterns hint at ancient, shared roots? The discovery of sweet potatoes, a New World crop, in prehistoric Polynesian sites, and of chicken bones, potentially of Polynesian origin, in pre-Columbian Chile, suggests that transoceanic contact, however sporadic, was within the realm of possibility. If people and plants could cross, why not ideas? A master stonemason traveling with a trading vessel could have carried the principles of a technique that would then be adapted to local stone and local gods. Weighing these two sides requires looking at the evidence without fantasy. The isolationist view is strengthened by the distinct differences that accompany the similarities. The Incas built without the wheel or strong draft animals. The Egyptians used both. The religious and symbolic systems surrounding these structures were utterly unique. This suggests deeply indigenous development. The diffusionist view, however, asks us to consider the sheer specificity of some techniques. The stone knob, the beveled edge, the use of diorite pounding stones for shaping granite. These are not universal, obvious solutions. They are highly refined tricks of a trade. Is it more likely that this specific trick was invented dozens of times independently, or that it was discovered once and then spread, changing and adapting along the way? The archaeological record, as it stands, does not provide a definitive answer. It offers a tantalizing puzzle where the pieces of evidence can be arranged to support either narrative. Perhaps the truth is not a choice between one or the other, but a spectrum. Some techniques may indeed be the natural offspring of physics and human need. Others, perhaps the most refined and subtle ones, might be the legacy of a long-forgotten dialogue between cultures, a whisper carried on the wind and waves that inspired builders across the globe to reach for the same impossible perfection. Perhaps the most compelling explanation lies not in a map but in a memory. Between the theories of isolated genius and direct cultural contact, a third possibility emerges, one that is both simpler and more profound. Some historians and philosophers of science point toward the concept of a primordial tradition. This is not a claim about a single, sunken super-civilization that taught everyone else. Instead, it imagines a deep, archaic layer of human understanding, a shared way of seeing the world that was common to our earliest ancestors. This foundational knowledge would have been an intimate, lived experience of natural law, an understanding of geometry born from observing the cycles of plants and stars, a sense of harmonics learned from the sounds of wind in caves or water over stone, and a practice of geomancy, or feeling the energy of the land itself. In this view, the first humans were not primitive in their perception. They were hyper-attuned to the patterns and forces of their environment. Building was not a separate act from this perception, it was its highest expression. When these early societies eventually dispersed across the globe, they carried this core, intuitive wisdom with them. It was not a written manual of techniques, but a shared philosophical and perceptual toolkit. Then, as groups settled into vastly different landscapes, the deserts of Egypt, the mountains of Peru, the forests of Cambodia, they began to apply this universal understanding to their local conditions. They asked the same fundamental questions of their environment, but the answers were shaped by the materials at hand. The core principle of stability might lead one culture to invent polygonal masonry to withstand earthquakes, while another might develop precise ashlar blocks to create eternal celestial alignments on flat ground. The shared goal was harmony between structure and earth, between human ritual and cosmic cycle. The techniques, therefore, were not copied blueprints. They were different dialects of the same deep architectural language. Think of it like music. A profound, emotional melody can be played on a grand piano in a concert hall, strummed on a guitar around a campfire, or expressed through a simple human voice. The instrument and the style change dramatically, but the core musical idea, the feeling it conveys, remains recognizable. The Great Pyramid, Sacsayhuamán, and the stones of Göbekli Tepe could be seen in the same light. They are regional interpretations of a universal human impulse to build meaning into the landscape, using the vocabulary of stone that their particular world provided. This perspective elegantly resolves the tension between the striking similarities and the distinct differences. It allows for true cultural independence. The Inca, the Egyptians, and the megalithic Europeans were absolutely unique civilizations with their own gods, languages, and social structures. Yet, it suggests they were all drawing from a much older, common well of intuitive knowledge about proportion, resonance, and placement. This knowledge may have been passed down not in textbooks, but through oral tradition, ritual, and the master-apprentice relationships of craftsmen over thousands of years. It was a living tradition, adapting and evolving, yet retaining its essential core. The evidence for this is subtle, woven into the fabric of myth and folk memory. Cultures worldwide share archetypal stories: a great flood, a axis mundi or world tree connecting earth and sky, a golden age of understanding. These are not histories of a specific place, but perhaps echoes of a shared psychological and perceptual origin. The primordial tradition hypothesis asks us to consider that the most sophisticated technology these builders possessed was not a tool, but a state of mind, a holistic way of being in the world that saw stone not as dead matter, but as a concentrated essence of the living earth, waiting to be awakened into form. If this is true, then every perfectly fitted stone is not a mystery to be solved, but a testament to a time when humanity listened to the world with a different ear and built its dreams in the language the earth itself taught them. The stones may have been placed to be heard as much as seen. Beyond their staggering visual presence, many of these ancient structures possess another, more elusive layer of design. They are instruments in the deep, subterranean chambers of Malta's hypogeum of Hal Saflieni, a complex carved from solid limestone over 5,000 years ago. Something extraordinary happens. Certain niches and rooms resonate at specific sound frequencies. A low chant or drumbeat made in one chamber can be felt and heard with uncanny clarity in another, creating an immersive sensory experience that modern researchers believe was central to the site's ritual use. This is not an isolated phenomenon. Studies within the granite confines of the King's Chamber in the Great Pyramid have detected a resonant frequency that some suggest could affect brainwave patterns, potentially inducing states of deep meditation or heightened awareness. The builders seem to understand that sound, shaped by stone, could become a tangible, transformative force. This acoustic intentionality points toward a worldview where construction was a form of tuning. Just as a master luthier shapes wood to produce a perfect note, these ancient engineers may have shaped caverns and corridors to amplify specific vibrations, turning the earth itself into a resonator for ceremony, healing, or communication with the unseen. The choice of dense igneous rock like granite or basalt was crucial here. These materials do not absorb sound, they reflect it, creating clear, sustained tones that can linger in the air. The precise angles and smooth surfaces were not just for visual appeal, they were acoustic mirrors, directing and focusing waves of energy through sacred space. Parallel to this science of sound is the ancient art of geomancy, the practice of reading and aligning with the invisible energies of the landscape. This concept is remarkably universal. In China, the tradition of feng shui for thousands of years has guided the placement of homes and tombs to harmonize with the flow of Kai, or life force, through the land. In the Andes, the Inca organized their entire empire around the Sec system, a radial array of 41 symbolic lines emanating from the Coricancha temple in Cusco. These lines connected hundreds of sacred spots called huacas, which could be springs, mountains, or unusual rock formations. The Secs were not physical roads, but pathways of ritual and cosmological meaning, mapping a spiritual geography onto the physical world. From the serpentine alignments of Britain's ley lines to the precise orientation of Egyptian temples, the pattern repeats. Structures were not placed at random on a convenient hilltop. They were carefully situated on sites believed to be nodes of terrestrial power, intersections where the energy of the earth was thought to be most accessible. Building with monumental stone, then, could be seen as an act of anchoring or amplifying that energy. The massive blocks drawn from the deep earth served as conduits or capacitors, grounding the celestial alignments above with the telluric currents below. Could this shared pursuit explain the cross-cultural obsession with such back-breaking construction? Perhaps the drive to move 100-ton stones was not solely about displaying political power or creating durable monuments. It may have been rooted in a profound, now lost empirical science, a science that perceived the earth as a living, pulsing entity and understood that certain stones in certain configurations at certain points could interact with that vitality. The perfect fitting of blocks might not have been just for earthquake resistance. It could have been to create a seamless energy circuit, preventing the leakage of a subtle force they sought to cultivate. We are left with a haunting possibility. The greatest architectural achievements of the ancient world might represent the fusion of three sophisticated disciplines: structural engineering, celestial astronomy, and a forgotten physics of earth energies and resonance. What we see as silent, static ruins may have once been humming, vibrant places of power, where the very stones were alive with sound and intention. This perspective does not diminish the practical genius of the builders. It expands it. It suggests they were not just masters of material, but also virtuosos of the invisible, composing symphonies in stone that played to both the eye and the soul. The mystery deepens from how they built to what they were truly building for. The silent perfection of these structures demands a final, human question. Who were the hands that achieved this? The evidence suggests these were not projects built by conscripted armies of unskilled laborers alone, but by the careful work of a specialized elite. a master class of builders who treated stonework as a sacred science. In ancient Egypt, the intellectual engines behind the monuments were the Sesh per Ankh, the scribes of the House of Life. These were not mere record keepers, but the nation's architects, engineers, and priests of knowledge, all rolled into one. They were the guardians of mathematics, astronomy, and the intricate rituals of construction. Their expertise was a closely held tradition, passed from master to apprentice within a closed, venerated guild. This was not a casual trade. It was a lifelong vocation that demanded a profound understanding of geometry, logistics, and the symbolic language of form. A similar story echoes in the Andes, where oral histories and early colonial records speak of the Colla, a people from the Lake Titicaca region, renowned as the finest stonemasons in the empire. The Inca would reportedly relocate entire communities of Colla craftsmen to work on their most important projects, valuing their skills as a supreme state resource. This pattern of specialization is the key. It transforms a mystery of how into a story of who. When a craft becomes the lifelong focus of a specific group, knowledge ceases to be a collection of simple tricks. It deepens into a true discipline. Techniques are refined over decades, not just years. Failures and successes become accumulated data, a kind of living library of practical physics. A master mason does not just know how to cut a stone. He understands how that particular type of granite will fracture under a specific angle of force, or how the morning sun will affect the expansion of a sandstone joint. This generational depth of practical wisdom is what could produce the breathtaking consistency and precision we see across entire sites. It also creates a fascinating, realistic possibility for the spread of such advanced knowledge. Highly skilled artisans were valuable commodities in the ancient world. They could travel as respected experts, hired by a foreign king eager to build a legacy. Think of a master sculptor from Greece being invited to work in Persia. More darkly, they could also be taken as prizes of war, compelled to apply their skills for a new master. The movement of these specialized individuals, whether voluntary or forced, provides a plausible human-scale vector for the transfer of complex techniques. A single master from one tradition, working alongside local apprentices in a new land, could seed ideas that would then blend with local methods and materials, creating a hybrid style. This is not about a lost civilization handing down a complete blueprint. It is about the quiet migration of genius, one craftsman at a time. The difficulty, of course, is proof. Stone does not bear the signature of its carver, but when we see the same subtle, non-obvious solution like the beveled edge or the integrated stone knob appear in two distant cultures, we are left to wonder. Was it independent invention, born of facing the same material challenge? Or could it be the faint echo of a master's teaching, adapted and passed down through new apprentices in a foreign land, their original names and homes long forgotten? The guilds are silent, but their legacy is written in the seamless joints of 1,000 stones, a testament to the power of concentrated human knowledge passed carefully from one generation to the next. A stone wall is a statement of possession, but a mountain reshaped into a temple is a declaration of divinity. To truly understand why cultures chose this most arduous path, we must listen to what the stone itself symbolized. Across the ancient world, from the cold moors of northern Europe to the sun-baked plains of Mesopotamia, stone carried a profound, shared meaning. It was the element of eternity. Unlike wood that rots or clay that crumbles, stone endures. It is the very bones of the earth, the most permanent material our ancestors could conceive of. To build with it was to tap into that timelessness, to create a work that would outlive dynasties, languages, and even gods. This was not merely practical. It was deeply philosophical. A society that invested generations in a stone monument was making a claim not just on the land, but on the future itself. They were planting a flag in eternity, declaring, "We were here, and our will is as enduring as the bedrock." This drive for permanence was intimately tied to concepts of power and the sacred. When a pharaoh commissioned his pyramid or an Inca emperor ordered the walls of Sacsayhuamán, they were doing more than building a tomb or a fortress. They were constructing a permanent physical manifestation of their divine mandate. The ruler's authority, believed to be granted by the gods or the cosmos, was literally set in stone. The immovability of the structure mirrored the perceived immutability of their power and their connection to the celestial order. The technical mastery we marvel at, the perfect joints, the seismic resilience, the celestial alignments served this higher symbolic purpose. A wall that could not be toppled by man or nature was the ultimate metaphor for an unshakable reign. A temple doorway that captured the solstice sun was proof of a king's privileged dialogue with the heavens. The engineering was in service of the ideology, but the symbolism reaches even deeper into the realm of memory and ancestry. In many cultures, prominent stones or outcrops were seen as the resting places of ancestors or as points where the spirit world touched our own. By incorporating these sacred stones or by quarrying new ones from the heart of the mountain, builders were creating a bridge between the living community, the ancestral past, and the enduring earth. The structure became a conduit, a place where time collapsed. This may explain the obsessive focus on techniques that made buildings seem impervious to decay. Polygonal walls that settle but never collapse, ashlar blocks fitted so tightly they appear grown rather than built. These were not just displays of skill. They were attempts to create something that transcended the human realm altogether, something that belonged to the geological timescale of the planet. When we view these parallels through the lens of shared symbolism, the global echoes become more understandable. Different cultures, yearning to express similar concepts of eternal power, divine connection, and ancestral veneration, were drawn to the same medium, monumental stone. And once committed to that medium, they were inevitably funneled towards similar technical solutions by the unyielding laws of physics and material science. The desire to create a symbol that would last forever naturally led to the pursuit of the most stable forms, the most durable joints, and the most precise alignments. The spiritual imperative demanded engineering excellence. So, the next time you see a photograph of those impossible Inca walls or the stark profile of a pyramid against the sky, look beyond the sheer scale. See them as philosophical arguments made solid. They are three-dimensional prayers for immortality, declarations of order in a chaotic world, and handshakes with eternity, carved by human hands from the bones of the earth. This shared language of stone suggests that perhaps the deepest connection between these cultures was not a shared blueprint, but a shared dream. The dream of leaving a mark so permanent, it would whisper their truths to the wind for all time. Two iconic sites separated by an ocean and thousands of years offer a perfect test for our theories. On the Giza plateau, the Great Pyramid rises from the Egyptian desert, a geometric mountain of roughly shaped limestone core blocks. Yet within its heart, the king's chamber is built from immense polished granite slabs, fitted with a precision that feels almost clinical. Half a world away, crowning a hill above Cusco, the fortress of Sacsayhuamán presents a different vision. Its famous zigzag walls are a mosaic of colossal limestone polygons, each one a unique piece of a gargantuan, three-dimensional puzzle. At first glance, they could not look more different. One is the epitome of angular, monumental simplicity. The other is a symphony of organic, interlocking complexity. But when we look closer, past the surface style to the underlying principles, the parallels become impossible to ignore. Both are staggering exercises in mass and precision, a combination that defies simple explanation. The Great Pyramid's core contains an estimated 2.3 million blocks, each weighing an average of 2.5 tons. The logistics of quarrying, transporting, and stacking that volume of material is a feat of such immense coordinated effort that it still boggles the mind. Sacsayhuamán, while smaller in total volume, ups the ante on individual stone size. Its largest block is estimated to weigh over 120 tons. Moving such a monolith up a steep mountainside represents a challenge of similar magnitude, just solved with a different topographic puzzle. So both cultures willingly chose the path of maximum difficulty. But they didn't just move big rocks, they mastered them. The granite coffer inside the king's chamber is hollowed from a single block of stone, its interior corners perfectly square, its surfaces flawlessly flat. At Sacsayhuamán, the joints between the polygonal blocks are so exact that after centuries of earthquakes, you still cannot insert the edge of a credit card between them. In both places, brute force was married to a surgeon's touch. Their purpose, too, speaks a similar language of power and cosmos. The Great Pyramid was the eternal resting place of a pharaoh, a god-king whose authority was meant to be as permanent as the stone itself. Its sides are aligned to the cardinal directions with minute accuracy, and its internal shafts point to specific stars, tethering the structure to the eternal cycles of the night sky. Sacsayhuamán, while a fortress, was also a paramount ceremonial site for the Inca emperor. Its zigzag walls are often interpreted as representing the teeth of the puma, a sacred animal, and its layout and orientation are deeply tied to Inca cosmology and solar observations. Both were far more than buildings. They were the ultimate symbols of a ruler's divine mandate, engineered to endure and aligned to claim a place in the celestial order. Yet, for all these profound similarities in ambition and achievement, the methods of assembly are distinctly their own. The Egyptian approach, seen in the pyramid's core, leans toward repetitive, massive simplicity. The blocks are largely rectangular, stacked in horizontal courses. The genius lies in the organization, in the ramps, the leveling, and the sheer scale of the workflow. The precision is reserved for the interior chambers and the dazzling, now lost casing stones. The Inca approach is almost the opposite. They embraced complexity from the very first stone. Each block was individually shaped to fit only its specific neighbors, creating a wall with no straight lines or repetitive patterns. Their precision is not layered on top of the mass. It is woven into its very fabric. One method speaks of centralized hierarchical control executing a single grand design. The other speaks of adaptable, localized genius solving a dynamic, irregular problem. This side-by-side view is illuminating. It argues powerfully against the idea of a single, identical instruction manual carried across the globe. The Egyptians did not build zigzag walls. The Inca did not build smooth-sided pyramids. Their aesthetic and structural languages are unique cultural signatures, but the comparison also makes a compelling case for a profound convergence of human purpose. Faced with the same desire to create an indestructible symbol of cosmic and royal power, two brilliant cultures looked at their own landscapes, their own materials, and their own spiritual beliefs, and arrived at two different yet equally breathtaking answers to the same eternal question. One chose the pure, singular form. The other chose the resilient, interconnected web. Both, in their own way, succeeded in making a mountain speak. The human face, carved in stone and scaled to the size of a house, appears as a haunting echo across the globe. On the remote, wind-swept island of Rapa Nui, the monolithic moai stand with their solemn, elongated gaze turned inland. Far across the Pacific, in the humid lowlands of ancient Mesoamerica, the Olmec civilization left behind a gallery of colossal stone heads with broad, powerful features and enigmatic helmets. These are not just statues, they are portraits of presence engineered on a scale that defies ordinary human experience. Separated by over 10,000 kilometers of open ocean, these two cultures never met, yet they dedicated immense resources to solving the same artistic and logistical puzzle. how to make a mountain bear a human likeness, and how to make that likeness stand for eternity. Technical parallels are immediately striking. Both projects began with a deep, intimate knowledge of the local stone. The Rapa Nui people quarried their moai from the volcanic tuff of the Rono Raraku crater, a relatively soft rock that allowed for detailed carving. The Olmec sourced their massive heads from basalt, an incredibly hard volcanic stone, hauling it from distant mountain quarries in the Tuxtlas Range to their ceremonial centers. In each case, the sculptors first shaped the basic form directly in the quarry, freeing the multi-ton mass from the living rock before the truly perilous journey began. The moai, some weighing over 80 tons, then had to be moved up to 18 kilometers across rugged terrain to their coastal stone platforms called ahu. The Olmec heads, some weighing 20 tons or more, were transported through swamps and rivers over distances of up to 100 kilometers. The scale of the transportation challenge alone represents a monumental commitment of communal labor and ingenuity. The methods of movement, while adapted to their unique landscapes, again reflect that universal human ingenuity in the face of gravity. For the moai, compelling evidence from oral tradition and modern experiments supports the idea of a dynamic, upright transport. Using a system of ropes, teams could have rocked the statues from side to side, effectively walking them to their destinations in a slow, rhythmic procession. For the Olmec, moving the dense basalt heads likely involved a combination of log rollers, sledges, and possibly water transport along rivers, leveraging the landscape as a pathway. Both solutions, though different, required extraordinary coordination and a shared, unwavering vision. Once at their sacred sites, the final act of raising these giants presented another shared engineering feat. The moai were carefully levered up stone ramps onto their ahu platforms, their backs to the sea, forever watching over the community. The Olmec heads were placed in ritual precincts, often arranged in lines or groups, facing outward as eternal sentinels. This act of erection was the culmination of the process, transforming a carved rock into an installed monument, a permanent part of the social and spiritual landscape. Where they diverge powerfully is in their artistic language and specific cultural message. The moai are highly stylized with elongated noses, strong brows, and minimalist bodies, believed by most scholars to represent deified ancestral chiefs, their power protecting the living. The Olmec heads are intensely naturalistic, depicting individual rulers with distinct facial features, fleshy cheeks, and detailed headgear, likely glorifying the authority of specific kings. One culture chose abstraction to represent a lineage, the other chose portraiture to immortalize an individual. This difference is profound. It speaks to unique worldviews and political structures. Yet this very divergence makes the core similarity all the more compelling. Despite different styles, different materials, and different beliefs, both cultures felt the same irresistible drive to translate human authority into the most permanent medium available. They chose stone, and they chose a scale that demanded a society's full effort. This suggests that the impulse to monumentalize, to take that which is fleeting and make it endure, to take human leadership and project it onto a geological timescale, is a deep, recurring theme in the human story. It is a theme that appears not through copied blueprints, but through a shared understanding that to make something truly important, you must build it to outlast the wind, the rain, and the memory of those who first looked upon it. The silent faces of Rapa Nui and San Lorenzo ask us not who taught them, but why this particular dream of stone seems to rise again and again from the human heart. Metal offers a secret to perfection that stone seems to deny. In fine metal casting, artisans have long used the lost wax method. They sculpt their intricate design in wax, encase it in clay, then fire it. The wax melts and drains away, leaving a perfect hollow mold into which molten metal is poured. The result is a flawless, detailed object, a one-to-one copy of the original wax model. This process allows for incredible complexity and, critically, for exact replication. Could the ancient stone masters have adapted this core principle, not for pouring but for carving? It is a speculative idea, but one that elegantly addresses one of the most perplexing aspects of certain ancient sites: the replication of perfect, complex shapes. Look at the famous 12-angle stone in Cusco, Peru. It is a masterpiece of polygonal masonry, a single block with 12 distinct sides, each one perfectly beveled to match the contours of the 11 different stones that surround it. The precision is such that it feels less like carving and more like a three-dimensional puzzle piece stamped from a mold. Or consider the mysterious stone boxes in the Serapeum of Saqqara, Egypt. Their interiors are so smoothly hollowed, with such sharp, consistent internal corners, that creating them by hand with simple abrasives seems a task of almost superhuman consistency. How did a worker, deep inside a dark granite box, ensure every surface met at a perfect 90-degree angle over and over again? The speculative theory proposes a potential answer: a template system. Imagine a craftsman first creating the desired shape, perhaps the complex negative space for a joint, in a malleable material like clay or even a harder plaster. This would become the master template, the negative form. To carve the stone, workers would not be measuring and chiseling blindly. Instead, they could use this template as a physical guide. They might press it into a softer intermediary material to create a temporary mold, or use it with a pointing machine, a simple device that transfers three-dimensional points from a model to a stone block. Some even suggest the use of a kind of slurry or cement that could be poured around a finished stone to capture its exact shape, creating a reusable mold for its neighbor. This would explain the incredible mirror image fits. If you need block B to fit perfectly against the irregular face of block A, you don't just measure block A. You take a direct impression of it. The resulting template guarantees that block B will be its perfect counterpart every time. The implications of such a technique, if it existed, are profound. It would represent a bridge between the worlds of sculpture and industrial replication. It turns a unique act of artistry into a repeatable technical process. A master could create one perfect prototype, and then teams of apprentices could accurately reproduce its form using the template, ensuring consistency across an entire temple wall or a series of identical stone boxes. This would also make the knowledge highly transferable, the core idea capturing a shape in a malleable medium to guide work on a hard one is a concept, not a specific tool. It could travel. A master from one culture could explain the principle to apprentices in another, who would then adapt it to their local stone and styles. While no direct archaeological evidence for such a stoneworking template system has been conclusively identified, the absence of evidence is not evidence of absence. Organic materials like wood, leather, or hardened clay used for such purposes would decay over millennia, leaving no trace. The theory remains in the realm of fascinating possibility, a ghost in the machine of history. It asks us to look at these impossible fits not as miracles of freehand carving, but as potential products of a sophisticated, systematic approach, a lost wax method for the age of stone, where the mold was not for pouring, but for guiding the hand that would reveal the form sleeping within the rock. Geography writes the first draft of every building code. The stones a culture could use, the tools they could forge, and even the weather they worked under were not mere backdrops to their ambition. They were active collaborators and sometimes stern teachers in the development of technique. This environmental lens reveals why the universal dream of building in stone took on such beautifully different forms. In Mesopotamia, the land between the rivers, the story was written in mud. The vast alluvial plains offered little in the way of durable stone, but an endless supply of fine clay. Here, the genius was not in carving mountains, but in baking them. They perfected the art of the mud brick, sun-dried or kiln-fired, and built their ziggurats, those stepped pyramids reaching for the heavens from millions of these uniform, man-made blocks. Their monumental architecture was an act of alchemy, transforming soft earth into enduring form. Contrast this with the world of the Inca or the ancient Egyptians. Their homelands were geological treasure troves. The Andes are a spine of volcanic and metamorphic rock, offering granite, andesite, and basalt. Egypt's eastern deserts yielded magnificent limestone and granite. When your very mountains are made of building material, your relationship with stone becomes intimate, and your techniques evolve to master it. You learn how each type fractures, how it sounds when struck, which way its grain runs. Stone mastery in these regions was not a choice. It was the only language the landscape spoke. The environment did more than provide materials. It presented specific, often brutal, engineering challenges that directly shaped method. Consider the icy, high-altitude passes of the Andes. Moving a 100-ton granite block up a steep, rugged mountainside is difficult enough. Now imagine doing it without the wheel, without strong draft animals. Researchers have proposed that the ingenious solution may have been hiding in the climate itself. During the cold night, workers could dampen the earthen path ahead. By morning, a thin layer of ice would form, creating a slick, low-friction surface. A stone on wooden sledges could then be pulled with dramatically less effort, gliding almost like a sled on a frozen pond. Similarly, the use of wet clay as a lubricant, a technique depicted in ancient Egypt, takes on new meaning in a dry desert. The slurry reduced friction on sandy causeways, but it also helped bind the sand together, creating a firmer temporary roadway. These were not random discoveries. They were brilliant adaptations born from close observation of local conditions. The builders asked the same question, how do we reduce friction, and found the answer in the mud at their feet or the frost on the morning grass. This principle extends to the very form of the structures. In earthquake-prone regions like Peru or Japan, the polygonal, interlocking wall was not just an aesthetic preference. It was a survival technology. The irregular, jigsaw-like joints allowed the wall to flex and settle during tremors, dissipating energy throughout the structure. In more geologically stable Egypt, where seismic activity was far less a concern, builders could prioritize perfect, stable alignments and smooth, continuous surfaces. The pyramid's form is one of pure, static mass. The Andean wall is a dynamic, resilient web. Both are masterpieces of engineering, but each is a direct response to the personality of the land it sits upon. Even the choice of quarry sites reveals this deep environmental logic. Why drag stone 100 miles if you can find it closer? Often, they did not. The specific type of stone mattered. The red granite of Aswan, the black basalt of certain volcanoes, the rose-colored rhyolite of a particular Andean valley. These were selected for their color, their durability, or their symbolic connection to the earth's power. The journey of the stone, therefore, was part of its meaning, a testament to the value placed on that specific piece of the world. So, when we see the global tapestry of monumental building, we are not looking at a single pattern copied under different skies. We are witnessing a grand, global conversation between human imagination and earthly reality. The universal desire to create something eternal, to honor the divine, to project power was the constant. The local environment provided the vocabulary. Abundant clay gave rise to the baked brick. Seismic lands inspired the living, shifting wall. Icy slopes suggested frozen highways for stone. This environmental lens does not diminish the genius of these cultures. It grounds it. It shows that their brilliance was not in ignoring the constraints of their world, but in listening to them so closely that they could turn obstacle into advantage. The diversity of techniques, then, is not a mark of separation, but of deep, intelligent engagement. Each culture solved the equation of monumentality using the variables provided by their own unique slice of the planet. The stone itself may have been the common dream, but the soil, the climate, and the very bones of the mountains dictated how that dream would finally take shape. This mastery of stone did not last forever. Across the ancient world, the age of the megalithic giants came to a close. In Egypt, the pharaohs stopped raising pyramids, turning their efforts to rock-cut tombs and grand temples built with smaller, more manageable blocks. On the isolated shores of Easter Island, the last of the great moai were left unfinished in their quarries, the knowledge of their transport and erection fading into legend. Around the Mediterranean, the colossal, irregular stones of the Mycenaeans gave way to the more refined but smaller marble columns of classical Greece. A profound shift occurred, and the question of why is as haunting as the silent ruins themselves. Did these cultures simply forget how to build this way? The answer is not a single event, but a slow unraveling of the very conditions that made such monumental work possible. Often, the most straightforward explanation is the exhaustion of resources. The quarrying and transport of megaliths consumed staggering amounts of timber for fuel, rollers, and levers. On islands like Easter Island, evidence strongly suggests that deforestation reached a critical point. Without wood to build sledges, rollers, or the frameworks needed to erect statues, the physical means to continue the tradition literally vanished with the last tree. In other regions, the most accessible and highest quality stone deposits may have been depleted, forcing a turn to alternative, smaller-scale materials. Yet, material scarcity alone does not explain the loss of the knowledge itself. The deeper cause likely lies in the social and spiritual fabric that wove these projects together. Megalithic building was not a standalone industry. It was the ultimate expression of a certain kind of society, one with a highly centralized authority, a vast pool of coordinated labor, and a unifying religious or ideological vision powerful enough to justify decades of back-breaking effort. When that social cohesion fractured through internal conflict, environmental hardship, or the arrival of new ideas, the institutional engine for such projects stalled. The master builders, their knowledge passed orally from teacher to apprentice within closed guilds, found themselves without patrons. Their students had no great walls to practice on. In just a generation or two, the nuanced, hands-on wisdom of how to listen to a stone's grain, how to judge the perfect bevel, or how to orchestrate the walking of a statue could fade into half-remembered stories. Furthermore, the very purpose of building underwent a transformation. New religious movements often rejected the old symbols of power. The rise of philosophies that focused on the individual soul or a less tangible God might have made the construction of mountains for the dead seem excessive or even misguided. At the same time, new technologies offered different paths. The development of strong mortars, the perfection of the arch, and the efficient use of brick allowed societies to create vast, beautiful spaces faster and with less centralized control. Why spend 50 years fitting a polygonal wall when you could build a soaring cathedral in the same time using smaller stones and a clever binder? The new methods were not necessarily better in terms of longevity. Many ancient mortar-free walls still stand while medieval ones crumble, but they were more adaptable to changing social and economic realities. This decline adds a poignant layer to the mystery of cross-cultural origins. It suggests that this advanced knowledge was not a permanent fixture of human progress, but a fragile bloom. It required a rare and specific convergence of stable resources, absolute purpose, and uninterrupted tradition. Its disappearance across so many cultures hints that it was never a widespread common knowledge. It was a specialized, elite craft, a peak of human endeavor that proved as vulnerable to the tides of history as any dynasty. The silence that followed the last placed stone is a reminder that progress is not always a straight line upward. Sometimes the most sophisticated answers are lost, leaving only their breathtaking questions etched in the landscape for us to wonder at. The silence of the stones has finally been broken by the sound of modern tools and determined voices. To move beyond theory, a new breed of investigator has taken to the field, not with shovels but with ropes, logs, and raw human effort. These are not treasure hunters, but experimental archaeologists and engineers who ask a simple, profound question. Can we do it ourselves? By attempting to replicate ancient feats using only the tools and materials presumed to be available, they transform abstract mystery into a tangible, physical puzzle. The results are often humbling, occasionally astonishing, and always illuminating. When a dedicated team on Easter Island successfully walked a full-scale moe replica hundreds of meters using only ropes and rhythmic coordination, they did more than prove a legend possible. They felt the immense, living weight of the stone, the precise timing needed in every pull, and the sheer communal focus required to prevent catastrophic collapse. This was not a stunt, it was a visceral lesson in the physics of belief. Similarly, projects focused on building even a small section of a pyramid wall using ramps, sledges, and wet clay lubricant reveal a hidden truth about ancient methods. What looks impossibly slow and arduous to our modern eyes often conceals a deep, embedded efficiency. The wet clay doesn't just reduce friction, it creates a renewable, self-leveling roadway. A team of 20 moving in a coordinated rhythm can generate a sustained pulling force that makes a several-ton block seem to glide. These experiments consistently show that the ancient methods were not brute force madness. They were refined systems where every action was multiplied by clever mechanics and synchronized labor. The true revelation, however, is the immense skill flaw these tasks demand. It is one thing to understand the principle of a stone knob as a lifting point. It is another to expertly tie a complex knot that won't slip under 50 tons of pressure, or to know the exact moment to place a wooden lever to initiate a controlled pivot. Modern attempts often fail on the first, 5th, or 20th try. Success comes only after painstaking practice, after learning to listen to the creak of the ropes and the subtle shift of the stone's weight. This trial and error process in the modern day reinforces a central idea from the past. These were not jobs for a temporary workforce. They required the practiced hands and ingrained intuition of specialists, of master artisans for whom these techniques were a second nature honed over a lifetime. These reconstructions serve as a powerful bridge. They take the grand, silent spectacle of a pyramid or a moe and break it down into a sequence of solvable, human-scale problems. They demonstrate that the cross-cultural parallels we see, the use of lubricants, the value of rounded transport paths, the importance of integrated handles, are not mystical secrets, but the logical outcomes of intelligent people wrestling with the same immutable laws of physics. Watching a stone walk or slide or rise into place through these experiments does something remarkable. It demystifies the monument while elevating the maker. The gap between our time and theirs narrows, not because the achievement shrinks, but because we begin to feel the shared strain in our own muscles, to hear the shared chant of coordinated effort, and to understand that the true miracle was not in defying nature, but in collaborating with it so completely. Roman roads and aqueducts were built with concrete, but for their most important monuments they still turned to the stone. The enduring legacy of those ancient, cross-cultural techniques is not a dead end, but a living foundation. The principles of mass, precision, and proportion, perfected in isolation across the globe, did not vanish with the cultures that birthed them. They were picked up, studied, and adapted, becoming the bedrock upon which later civilizations built their own dreams of permanence. Consider the pragmatic genius of Roman engineering. While they revolutionized construction with their concrete, allowing for vast, fluid spaces like the Pantheon's dome, they reserved the most monumental statement for cut stone. The foundational layers of the Colosseum, the immense blocks of the temple of Jupiter Optimus Maximus, even the precise ashlar work of later imperial forums, all speak a direct physical lineage to the Egyptian and Greek masters of stone before them. The Romans understood that for sheer symbolic weight and timeless endurance, there was no substitute for a perfectly fitted megalith. This knowledge was a living inheritance, passed down through guilds of masons whose tools and techniques evolved, but whose core respect for the material remained. When the Roman world transformed, that knowledge did not disappear. It found a new sanctuary and a new purpose within the walls of the medieval cathedral. The master masons who raised charters or Notre Dame were the direct intellectual descendants of those ancient builders. They worked in a new language of faith, with pointed arches and flying buttresses, but the grammar was written in stone. The precision required to carve 1,000 unique keystones for a vaulted ceiling, or to fit the complex tracery of a rose window, demanded the same intimate understanding of geometry, stress, and material that shaped a polygonal wall in Peru. The Cathedral Building Lodge was a university of stone, where the old secrets of lifting, fitting, and aligning were preserved and pushed to new, dizzying heights. This legacy is not merely historical, it is actively consulted in the present day. In regions plagued by earthquakes, modern engineers have turned their attention to the ancient walls of the Inca. They study the way those irregular polygons lock together, creating a structure that dances with seismic waves rather than fighting them. The principle of allowing controlled movement within a rigid frame is a cornerstone of modern base isolation technology, used in everything from skyscrapers to bridges. The ancient solution, born of necessity and deep observation, provides elegant, time-tested data for contemporary problems. It is a conversation across centuries where a modern computer model validates the intuition of a master stonemason from 1,000 years ago. The story of these techniques, therefore, is not one of a forgotten golden age. It is a story of continuous adaptation. The foundational vocabulary of monumental building, the idea that stability comes from perfect fit, that permanence requires a dialogue with the landscape, and that beauty is a function of precise mathematics, was established in those scattered, ancient sites. This vocabulary was never owned by one culture. It was a shared human discovery, a set of tools that proved so effective, so fundamentally true to the laws of physics and human aspiration, that it became indispensable. Each successive civilization added its own dialect, its own stylistic flourishes and technical innovations, but the core grammar remained. So when we look at a Gothic spire piercing the sky, or a modern seismic damper hidden within a tower's core, we are not looking at a break from the past. We are seeing the latest sentence written in a very old, very resilient language. The stones of Sacsayhuamán, the pyramids of Giza, and the monoliths of Göbekli Tepe were not final statements. They were the first powerful chapters in an ongoing story of how humanity builds its hopes into the bones of the world. The archaeological record is not a simple story, and the ideas we have explored exist within a fierce and necessary debate. Mainstream scholarship approaches these global parallels with deep skepticism, and their perspective is built on a foundation of rigorous evidence. They point out correctly that the timelines are staggeringly vast. The Great Pyramids of Giza were ancient ruins, already thousands of years old, by the time the first stones of Machu Picchu were ever set in place. To suggest a direct transfer of technique across such an immense gulf of time and space requires extraordinary proof. To date, that definitive proof, a tangible artifact, a shared inscription, or an unmistakable tool signature found across these oceans remains elusive. The primary concern from this academic viewpoint is the integrity of individual cultures. To attribute the breathtaking achievements of the Inca or the ancient Egyptians to some outside, often vaguely defined source risks diminishing their own innate genius. It can unintentionally echo outdated colonial ideas that indigenous peoples were incapable of such innovation on their own. This pushback is not about closing doors, but about demanding a high standard of evidence before redrawing the maps of human history. They argue that the similarities we see are often overstated, or that they represent the logical, independent conclusions of brilliant minds solving similar problems with the same laws of physics. The cohesive, mortar-free wall is an elegant solution to seismic activity, a solution that could be discovered by any culture living on unstable ground through generations of trial and observation. In this light, the quest for a single, lost teacher can distract us from appreciating the unique, organic development of each civilization. This critical stance serves as an essential anchor, reminding us that wonder must be tempered with careful scrutiny. It frames diffusionist ideas not as established facts, but as compelling hypotheses awaiting validation. A responsible exploration sits in this tension, acknowledging the mystery in the stonework while respecting the complexity and the profound, separate journeys of the cultures that shaped it. The true story may be less about a shared blueprint and more about the incredible capacity of the human mind, in isolation after isolation, to reach for the same monumental heights. Without a single written blueprint, the most sophisticated engineering knowledge of the ancient world walked a fragile tightrope across the generations. It was carried not on papyrus or clay tablet, but on the human voice woven into the very fabric of story and song. The legends that survived are often our only glimpse into the builder's mind, and they are rarely straightforward. High in the Andes, a persistent myth tells of a time when the great stones of Sacsayhuamán were not dragged, but made pliable. The story says the builders possessed a magical plant whose juices, when applied to the rock, would soften its surface like clay, allowing them to mold the edges to a perfect fit. To a modern ear, it sounds like pure fantasy, but listen closer. Could this be a metaphorical recipe, a way of preserving a chemical process? Certain plants in the region, like the sap of the puya or other native species, are highly acidic. Applied to a stone surface, such a substance could actually etch and soften the crystalline structure, making it easier to abrade and shape with simple tools. The magical plant may not have made stone liquid, but it could have made it more workable, a vital technical secret encoded as a tale of supernatural aid. Across the Atlantic, in the misty hills of Celtic Britain, folklore speaks of the giants of old who built stone circles. In some tales, the stones themselves are said to move at the command of a wizard's word, or to travel to their places at dawn when called by a specific sound. Again, the surface is magic. The underlying truth might be acoustics and coordination. The precise, rhythmic beating of drums, the blast of a horn, or even a specific chant could have served as a critical auditory signal for a large team of workers. On the count of the third drumbeat, everyone pulls. At the sound of the trumpet, everyone pushes. In the chaos of moving a multi-ton slab, a unified auditory command is far more effective than shouted orders lost in the wind. The story of stones moving to sound becomes a poetic, unforgettable way to teach the importance of rhythmic, coordinated labor, a core principle of megalithic transport. This pattern of encoding practical knowledge in narrative is a universal human technology, perhaps the most durable one we ever invented. Before widespread literacy, complex information had to be memorable to survive. A dry list of instructions, mix this plant, pull on that beat, would be forgotten in a generation. But a captivating story about a wizard who could command stones with a song, or a hero who discovered a plant that tamed the mountain's bones. That sticks. It gets retold around fires from elder to child, preserving the core idea within an engaging shell. The specific details of the how might blur or mythologize over centuries, but the essential concept remains. There is a way to make stone easier to work, and there is a power in synchronized sound. When we compare these myths across cultures, we are likely not uncovering a shared, hidden history of contact. Instead, we are witnessing a shared cognitive strategy. Cultures facing the same immense physical challenges: how to shape hard rock, how to organize hundreds of people, independently discovered that the best way to preserve their hard-won solutions was to turn them into legends. The Inca story of the softening plant and the Celtic tale of singing stones are not pages from the same lost manual. They are separate inventions of the same brilliant memory aid. This transforms these myths from mere curiosities into historical documents of a different kind. They are not records of what literally happened, but vessels of how things were done. They hold the distilled wisdom of the craft, disguised as magic to ensure it would never be lost. The next time you hear an ancient tale that seems too fantastical to be true, listen for the echo of the workshop within it. The magic might just be a metaphor waiting for us to learn its language. The legends are one form of evidence, but the stones themselves hold another, far more precise testimony. A quiet revolution is unfolding in the study of these ancient sites, one driven not by shovels but by lasers and algorithms. The future of this mystery is increasingly digital. Technologies like ground-penetrating radar and LiDAR are peering through soil and jungle canopy, revealing hidden quarry roads, lost ceremonial plazas, and the full, staggering extent of ancient engineering. More intimately, high-resolution three-dimensional laser scanning is capturing the surfaces of individual stones with sub-millimeter accuracy. Every chip, every bevel, every microscopic striation from a long-vanished tool is now being translated into a cloud of billions of data points. This creates a perfect, permanent digital record, a fingerprint of the stone itself. This data opens a door to a new kind of comparative analysis, one that moves the conversation from artistic impression to mathematical fact. Researchers can now take the digital scan of a granite block from Baalbek and compare its geometry, its surface wear patterns, and the angles of its tool marks with a similar scan of an andesite block from Ollantaytambo. They are searching for statistical signatures, for quantifiable patterns in the craftsmanship. Does the curvature of a specific type of drill hole match in both places, suggesting a similar tool or technique? Do the wear patterns on a particular style of stone knob indicate it was used for levering in an identical way? This is the search for a technical fingerprint, a repeatable, measurable signature of a specific method that might appear in two distant corners of the world. The promise of this approach is profound. It could one day move the debate from the realm of intriguing speculation into the domain of evidence-based connection. Imagine if analysis revealed that the specific angle of the beveled edge on certain Egyptian stones was statistically identical to that found on certain Peruvian stones, not just visually similar, but mathematically congruent within a tiny margin of error. Such a finding would be a thunderclap. It would suggest not just a shared idea, but a shared, standardized execution of that idea, something far harder to explain through independent invention alone. Conversely, if the digital signatures consistently show fundamental differences in technique despite visual similarities, it would powerfully support the theory of separate, convergent development. This technological lens does not favor one narrative over the other. It simply provides a new, more rigorous language for the inquiry. It transforms the silent dialogue between stones into a conversation of numbers and patterns, searching for the ghost in the machine of history. The stones have kept their secrets for millennia, but for the first time we are learning to listen to them in a way they might finally answer. So where does this leave our grand mystery? The truth of these cross-cultural origins is not a single, buried blueprint waiting to be unearthed. It is something far more complex and, in its own way, far more beautiful. It is a tapestry woven from several distinct but interconnected threads, each one essential to the final, breathtaking pattern we see across the globe. The first thread is the undeniable power of independent human ingenuity. When brilliant minds in isolation confront the same fundamental problems of physics, gravity, friction, material stress, they often arrive at similar, elegant solutions. The polygonal wall is a brilliant answer to seismic instability. The beveled edge is a logical way to protect a perfect corner during transport. These are not secrets whispered across oceans, but conclusions written in the universal language of cause and effect, discovered again and again by cultures who simply refused to be limited by the weight of a mountain. This thread speaks to a shared cognitive brilliance, a testament to what our species can achieve when purpose and persistence collide. Yet, another thread is the intimate dialogue with environment. Ingenuity does not happen in a vacuum. The specific form it takes is shaped by the local world. The Inca, moving stone up frozen Andean slopes, discovered ice as a lubricant. The Egyptians, working on vast desert plains, perfected the water and clay sled. The dream of monumentality was universal, but the methods were local dialects born from a deep listening to the land itself. This environmental thread explains the beautiful diversity within the similarity, why the solutions, while logically parallel, wear the distinct fingerprints of their homeland. Then there is the delicate, controversial thread of possible contact. The vast oceans were not necessarily absolute barriers. We know that plants, like the sweet potato, crossed the Pacific in pre-Columbian times. If a seed could travel, could an idea? It is not about sunken continents, but about the occasional chance meeting of seafarers, where a master mason on a trading vessel might share a single, brilliant principle, the concept of a template or the use of a specific lifting knot that then took root in a new land and blossomed into a unique tradition. This thread suggests a human network far more interconnected than our textbooks sometimes allow, where knowledge could travel in fragments, inspiring without dictating. Woven through all of these is the deepest, most profound thread, a shared symbolic and spiritual drive. Cultures separated by millennia and geography all felt the same compelling need to build for eternity, to anchor human aspiration to the timelessness of stone. This was not mere engineering, it was a philosophical and religious act. The perfect joint was a metaphor for cosmic order. The aligned temple was a machine for harmonizing with the heavens. This shared yearning for permanence and meaning created a powerful selective pressure. It demanded techniques that were not just functional but flawless, methods that could create a legacy meant to outlast the builders themselves. When you combine these threads, the mystery begins to resolve into a coherent, human-scale story. The striking similarities are not coincidental, but the result of different cultures asking the same ultimate questions of their world. The significant differences are not contradictions, but proof of their unique identities and adaptive genius. We are not looking at a single lost civilization teaching the world, nor are we looking at dozens of completely isolated miracles. We are witnessing convergent evolution in technology. Just as wings evolved independently in birds, bats, and insects to solve the problem of flight, so too did techniques of megalithic construction evolve independently to solve the universal human problems of weight, time, and meaning. The pyramid, the polygonal wall, the colossal head, these are different species of the same architectural genus, each perfectly adapted to its own cultural and environmental niche. This synthesis does not diminish the wonder. It grounds it in something real and enduring, the incredible recurring capacity of the human spirit. When faced with the raw material of the earth and the boundless scope of their dreams, people across the ancient world looked up and then they built. They built not because someone told them how, but because something within them, a mix of reverence, ambition, and sheer inventive brilliance, demanded that they try. The stones that fit without mortar are a testament to that universal drive, a silent chorus of different voices all singing the same eternal song of human possibility. The final stone is placed, but the story is far from over. Our journey from the sun-bleached pyramids to the cloud-ringed citadels leaves us not with a simple answer, but with a richer, more profound question. The evidence does not point to a single lost teacher, a forgotten map passed between continents. Instead, it reveals something more powerful, a recurring pattern in the human spirit itself. Across vast oceans and millennia, different cultures heard the same silent call, to take the bones of the earth and shape them into a statement meant to outlast empires. They dreamed the same dream of eternity, and then, with astonishing ingenuity, they found ways to make that dream solid. What we witness in these impossible walls and perfect alignments is not a mystery of contact, but a mystery of convergence. The human mind, when faced with the same fundamental challenges of weight, time, and meaning, often discovers the same elegant solutions. The interlocking wall that dances with earthquakes, the beveled edge that guides a giant block home, the celestial alignment that anchors a temple to the stars. These are not copied blueprints. They are the logical, beautiful conclusions written in the universal language of physics and profound ambition. These structures are not puzzles to be solved so much as they are mirrors held up to our own understanding. They challenge the modern assumption that advanced innovation requires a linear, connected progression. They show us that brilliance can bloom in isolation, that the same peak of achievement can be scaled from different sides of the mountain. The Great Pyramid and the walls of Sacsayhuamán do not whisper of a shared secret society. They roar with the separate, yet parallel, triumphs of human will and intellect. So perhaps the most valuable takeaway is this: we must expand our view of ancient possibility. Our ancestors were not primitive beings waiting for knowledge to arrive. They were keen observers, masterful engineers, and visionary artists who engaged in a deep, creative dialogue with their world. They listened to the stone, studied the sky, and organized their societies around a purpose grand enough to inspire generations of labor. The true connection between these cultures is not a thread of shared instruction, but a shared capacity for wonder and a shared refusal to be limited by what seems impossible. As you look at the images of these sites now, see them not as isolated marvels, but as chapters in a single, sprawling human story. A story about our enduring need to build meaning into the landscape, to reach for the divine, and to leave a mark that says we were here and what we dreamed was worthy of the mountain itself. The conversation continues with you. What do you believe lies behind these echoes in stone? Do you see the fingerprints of lost contact across the seas, or do you hear a chorus of independent genius, all singing the same monumental song? Share your perspective below, and for more journeys into the heart of history's greatest enigmas, be sure to subscribe.